If you've ever been on a NASCAR track like how I am right now, you'll notice that at the beginning of the race, you may be on a level ground and driving as fast as you can. Suddenly, as you're going around the turn, the ground is not level anymore. Instead, it starts tilting to one side. And in today's episode, we're going to be talking about that tilt, which is also known as a banked turn. A banked turn is effectively an incline of an elevation which helps you navigate around a corner. Now in these problems over here, you're usually given some values. For example, you might be given the mass of the vehicle. You might be given the angle of incline. You might also be given the speed that the vehicle is traveling at, or maybe this is what you're trying to look for. In any case, you want to be able to navigate around the turn without either sliding up or sliding down. Because if you drive too fast, from experience, if you ever played this game before, you're going to veer off towards the right and up the ramp, and you might fall off the ramp, and that's very dangerous. Or if you drive too slowly and it's an icy day, you may end up gliding down to the ditch, and that doesn't help you out either. So we'll start off with the first example of an icy condition. So this is one where you have to drive just fast enough that you can just navigate around the banked turn. For a free body diagram, again, you're not supposed to draw the ramp. I'm going to leave this here just for a reference sake, and I'll erase it afterwards, because we know that this ramp will be at an angle. The normal force is always perpendicular to the ramp. And the force of gravity, well, that just points straight downwards. Again, on an icy day, we don't have friction to help us out, so we don't need to draw any other vectors, and we're pretty much done with just this. One last thing, however, is that we want to include a coordinate system for the reader. So in this setup over here, although it may be tempting to draw a coordinate system that's in alignment and perpendicular to the ramp, it's actually a lot more efficient to solve these problems with a dimension that's either up into the sky, also the positive y dimension, and another one that's in the positive x dimension. And the reason for this is that we know that our centripetal acceleration has to be going towards the center of our turn. So as we're going around a turn, acceleration always points to the center. That's where the radius is as well. All right, so you're probably given a value of radius for the question. Okay. So let's start off with the icy condition version. One thing we want to do is we want to break down our normal force. Because we notice that our normal force, well, it does have a vertical component and it does have a horizontal component. Interestingly, the angle that we generate here is exactly the same as the angle of incline. And you can imagine that if this ramp was not as steep, well, this angle up here would also be less as well, down to the point where your Fn is equal and opposite to your Fg on a level surface. Okay, so we'll just leave it at this for a free body diagram. Okay, now let's create a formula to be able to readily predict how fast must you drive around this angle over here so you can make it around without accidentally gliding up the ramp or gliding down the ramp. First dimension we want to deal with is the y dimension, and the reason for that is that we know that our ff is equal to mu s Fn. Alright, so if there's any friction involved, we have to deal with the y dimension first. Luckily for us, we don't have any friction involved, but for the safetiness of these type of problems, you probably want to deal with the y dimension at the beginning. In the Fnet y dimension, it has to go to 0. And the reason why it needs to go to 0 is because we don't want a car that will fly off into the heavens, and we don't want a car to sink down into the ramp itself. So in the y dimension, it has to be equal to 0. We've already defined upwards as positive, so we can see that the normal force in the y dimension allows us to go up. Now this vertical component, you'll notice that it's beside theta, and that's why we're going to multiply the hypotenuse by the cosine of theta. Alright, so the hypotenuse of Fn times cosine of theta represents this blue vector right here. There's another blue vector that's pointing to the ground, and because it's in the opposite direction, that's why we're going to subtract Fg. To save some time, we know that Fg is also equal to mg. And here's our first statement. Now when we rearrange it, we'll have Fn is equal to mg all over cosine theta. Next, we'll move on to the x dimension. Again, we're dealing with centripetal acceleration, where we're accelerating towards the center of the turn. All right, so our F net x is going to be equal to ma centripetal acceleration. That's equal to anything that's helping you navigate to the center, which is this vector right up here. So MAC is equal to Fn times, and since it's opposite of theta, we're going to use sine of theta. So the hypotenuse times the sine of theta. Now, as for AC, there are three things we can sub into here, as you may have learned before. Centripetal acceleration can be equal to your speed squared over r, or it can also be equal to 4 pi squared r over period square, or it can also be equal to 4 pi squared r times f squared. And the choice that you use is based upon the problem that's given to you. Sometimes you're given the period of rotation, sometimes you're given the frequency of rotation, and sometimes you're just given the speed. So you'll sub in the one that helps you in solving the problem. In this case over here, since we're talking about a car that's going around a banked turn, we probably want to use this one over here. In other words, m v squared over r is equal to Fn times sine theta. Alright, now let's sub it in. So this is going to look like this. mg in the numerator. What else is in the numerator? Well, the sine theta from the original formula, and we'll have cosine theta in the denominator. At this point here, some of you have noticed that on both sides there's the mass. In other words, you don't even have to know about the mass of the vehicle, and that wasn't necessary as a given. Another thing is that some of you guys might notice that you have a sine over cosine, which is also equal to tangent. So this equation here can also be represented by v squared over r is equal to g times tan theta. And if this is a problem where we're trying to look for the speed that's necessary to navigate around the icy turn without accidentally sliding down or up the ramp, well then v will be equal to the root of r times g times the tan of theta. All done. Again, this is not an official formula. Instead, this is a derivation which got us to this final answer. Alright, so a formula like this will not be given to you on a test, and you need to derive it. In fact, the exercise that we've gone through here, where we started solving from our basic knowledge, this is known as solving through first principles. Solving using first principles is a way of solving a problem with given basic background knowledge of, for example, inclines, and F net is equal to ma, and centripetal acceleration. Now let's try a bit more challenging problem. This time around in our banked turn, let's say you drive as quickly as possible and there's friction involved and you don't want to accidentally fly off the edge of the ramp. To assist you, that's why you have the force of static friction, but that's going down the ramp. Okay, once again in a free body diagram, do not draw the ramp itself. I'm just going to dot it out just so that we can visually see what's going on, but it's not part of the official diagram. Gravity is always pointing downwards, and yeah, we're going to stick with blue as the positive y dimension, and we're going to use the red as our positive x dimension. Our normal force is neither vertical or horizontal. It's always going to be perpendicular to the ramp. It's always going to look like this. All right, but we're going to draw it on top of the box. Okay, so with all these vectors here, this is it for the free body diagram. However, it is helpful to know all the components of every vector. For example, the normal force, as it's pointing at a diagonal, well, there's a component of it that's pointing up vertically, and there's a component of it that's pointing towards the left. The angle that's generated, coincidentally, is equal to the angle of elevation of the ramp itself. The same is also true with static friction. You'll see the static friction also has a horizontal component, which actually helps it to experience centripetal acceleration, and there's also a vertical component as well, pointing downwards. It too also has a theta, which is also equal to the elevation of the ramp itself. With this basic diagram all drawn up for our references, again, everything in black is all you need for the free body diagram, and I've color-coded it so that we can see all the components involved. Since the formula for the force of static friction is equal to mu s times Fn, we have no choice but to deal with the y dimension first. As we mentioned before, F net y has to go to 0. Because we don't want a car to fly off into the heavens and we don't want it to sink into the ground. How do we accomplish this net value of 0? Well, it's equal to this vector here minus this vector pointing downwards minus the force of gravity. Alright, so it's Fn, but remember Fn is this black vector here. We want the blue vector, and since the blue vector is beside theta, we're going to multiply the hypotenuse by the cosine of theta. As for the force of static friction, You'll see that this blue vector over here is opposite of theta, so it's minus fs times the sine of theta. Lastly, we have fg, and fg is also equal to mg. Okay, now let's start cleaning this up. So 0 is equal to Fn times the cosine of theta, and we're going to drop this bad boy right into here. Right, so minus the force of static friction. Yeah, I could have used the letter S here if I wanted to, which is equal to mu s times Fn times the sine of theta minus mg. And you'll notice that since we have two Fn terms here, we could factor it out. So Fn open bracket cosine theta minus mu s times sine theta close bracket minus mg is equal to 0, or we can just simply bring mg over to the left hand side just to give us a head start on this problem here. That will tell us that if we want to solve for Fn, it's equal to mg divided by a bunch of stuff. And that will be our equation number 1. Next, we move into the x dimension, so f net x. F net x is equal to ma. And since it's centripetal acceleration, we can replace ac with v squared over r, as we're talking about as fast as possible. So speed around the turn with this given radius of the bank turn. All right, so mv squared over r is equal to whatever that allows it to centripetally accelerate towards the center, which are these two vectors here. This one here, and this second red vector over here. So that's equal to our Fn times, as the red vector is opposite of theta, Fn times the sine of theta. And as for static friction, well, you'll see that the static friction vector, this is beside theta, so we're going to multiply by the cosine of theta. Okay, next thing we're just going to clean it up one more time. We see that Fs is equal to mu s Fn, so I'm just going to sub that in there. Plus mu s times Fn times cosine of theta. And yeah, you could sub in this first equation right over here, and then once again right over here, but you can imagine the disaster that we're going to create by doing that. So before we go there, how about we just factor out the Fn, and you'll see that after we sub it in, it won't be as crazy looking. Plus mu s times cosine of theta, and that's equal to our mv squared over r. That's equation number 2. Alright, so let's sub 1 into 2. Okay, so mv squared over r is equal to, and in the original formula, we still have our sine theta in the numerator plus mu s times cosine theta in the numerator. But we also have some new friends now, right? We have mg at the top, and down below we have cosine theta minus mu s times sine theta. At this point here, some of us might have noticed that there's mass on both sides of the equal sign. In other words, in these problems over here, we don't care how light or how heavy the car is. The outcome's going to be exactly the same. So that's one interesting property. All right, so I guess the last step really is just to isolate for v. So v is equal to the root of r times g, so the planet does matter, the radius size does matter, multiplied by this very complicated looking formula, sine theta plus mu s times cosine theta, all over cosine theta minus mu s times sine theta. So as long as we know the angle, the coefficient of friction, the radius of the bank turn, and what planet we're doing this in, we can figure out the fastest speed that we can drive and navigate around this curve without accidentally flying off the ramp. Now we can also change this problem around, and it's a bank turn that you drive as slow as possible. Let's say it's a very snowy day, so the coefficient of friction is some rather small number. All right, so if you drive too slowly, sadly you're just going to drive into the ditch. So you have to drive just fast enough so that the friction will help you out and you can still navigate around. So yeah, that's our next problem. We're going to try to solve this as slow as possible. In fact, if you want, you can pause the video right now, try deriving it out, and then you can follow along with me afterwards. Okay, so this time around, we probably can predict the mass doesn't really matter, but we'll still have that as a formality, as it's part of the free body diagram. All right, we have the obligatory gravity that's pulling us downwards. Again, we want to stick with the color coding because it helps in visualizing, when to use cosine and when to use sine. All right, so blue vector will be the y dimension, and any red vectors will be the positive x direction, which is also our direction for our centripetal acceleration. That should always be positive. It's the way how you solve all these problems. Okay, so if we're driving as slow as possible, then the friction will be going up the ramp as we're slowly gliding down the ramp when we come to a rest, right? So the force of static friction will be pointing up. The normal force, as mentioned before, it is always perpendicular to the ramp, and that's why it's at this weird diagonal. Fg is already broken down to its vertical component. Let's go and break down the rest into their horizontal and vertical components as well. All right. So what you're really trying to do is that you're trying to draw, a line that's as horizontal as possible for both of these, and that's how you can solve for its corresponding horizontal component. And for the vertical component, again, you're just trying to draw a vector that's up and down. So that gets us there, and this gets us up there as well. As mentioned before, these two other triangles also share the same angle as the angle of elevation. Again, you can use your imagination and draw this as shallow as possible, and you'll notice that these angles over here will also diminish as well. Right? So there's our basic setup, and as I mentioned before, you want to deal with the vertical dimension first, just so that you can sub that formula in there. Okay, so f net y has to go to 0 because it doesn't need to fly into the sky or sink to the ground. That's equal to Fn times the cosine of theta plus Fs times the sine of theta. I hope you can see that. Fn times the cosine of theta, and this is opposite, so Fs times the sine of theta. Both of these are pointing upwards, that's why you get the plus treatment. Gravity, on the other hand, is pointing downwards, so it's minus Fg, or if you want to save some time, minus mg. We've mentioned earlier that Fs has the same meaning as mu s times Fn. And the easiest way to solve these problems really is just to factor out the normal force and then sub the equations together. Trying to do it any other way, it's doable, but it'll just take you quite a bit of time to get to your final answer. Okay, again, minus mg, when you bring it over, it becomes positive mg. So this will quickly tell you that Fn is equal to mg divided by cosine theta plus mu s times sine theta. Now, if you don't recall from earlier, this looks very similar to the previous formula, but this one has a plus sign over here, and the previous one has a minus sign. All right, so they are different equations. All right, after all, it is a different scenario. Okay, so that's equation number 1. In our f net in our x dimension, again, our f net is equal to ma, and since we're dealing with centripetal acceleration, that's pointing out over here, and velocity is involved, or speed is involved, sorry, then we'll use the formula mv squared over r as our f net. And the reason why we're traveling this direction is because of one vector, and the reason why we're not traveling that direction is because of another vector pointing in the opposite direction. Right? So make sure you get your signs filled in correctly here. So the first one is Fn times, and you can see that this red vector is opposite of the angle, this tiny little angle over here, and that's why it's Fn times the sine of theta. As for the second vector, again, it's pointing away, so it's not really helping us in our centripetal acceleration, and it'll get the minus treatment. So that's equal to Fs times the cosine of theta. We already stated that Fs has the same meaning as mu s Fn, so we'll sub that in. Fn times sine of theta minus mu s Fn times the cosine of theta. And as I said, to make our lives easier, instead of subbing in that ugly thing twice, once over here and once over here, we're just going to factor out Fn at this point. So Fn, open bracket, sine theta minus mu s times cosine of theta. And that's equal to mv squared over r. If we sub equation 1 into equation number 2, we'll end up with something that looks like this. So mv squared over r is equal to, we'll keep the original numerator, so sine theta minus mu s times cosine theta, And the new numerator has an mg, and we also have a cosine theta plus mu s times sine theta in the denominator. Yet once again, since both sides have an m, well, we don't care about the mass of the vehicle. Whether it's light or heavy, it's going to have the same exact outcome. And yeah, if we're trying to solve this problem for v, then v is equal to the root of r times g times, open bracket, sine theta minus mu s times cosine theta, close bracket, all divided by cosine theta plus mu s times sine theta. And I just want to check something because it's minus on top, plus down below. I think the other one had it flipped around. Yeah, that's one thing I noticed about these two problems. That part gets flipped around. Anywho, this equation over here, again, don't memorize it. I'm not interested in you memorizing it. Instead, I want you to show me how to derive these equations. All right, that's what's important. From first principles, how would you solve these type of problems? It doesn't have to do with regards to speed. It could also deal with frequency because you're spinning around and around and around in a bank turn track, racetrack, let's say. All right, so it could have been one of those problems as well. That's it for you today. And tonight's homework, again, just answer questions in the textbook as well as in the course pack. Best of luck in that, and I'll catch you in the next episode.